So, good morning everyone. For today, we are going to briefly explore the speed of sound, a fascinating journey through a pressure disturbance. But first, we are going to have a recap. So, what is sound? The sound is a form of energy created by vibrations. It is a mechanical wave, meaning it requires a medium, like air or water, to travel. The vibrations displace particles, and this energy is passed from one particle to the next. So, what is a sound wave? A sound wave is a propagating pressure disturbance. It consists of areas of high density, called compressions, and area of low density, called rarefactions. This alternating pattern is how sound waves move through a medium. So, this leads us to our curious topic for today, the speed of sound. So, what is the speed of sound? The speed of sound is the distance of sound waves travels per unit of time. The speed is constant for a given medium under the same conditions. The relation is defined by the formula B is equals to lambda times F, where V is speed, lambda is wavelength, and F is frequency, where the standard unit is meters per second. So lambda refers to the Greek letter which looks like an upside down Y. But there are also factors affecting the speed of sound. The two main factors affect the speed of sound. First is density. Sound travels faster in denser media because molecules are closer and can transfer energy more quickly. Second is temperature. As temperature increases, molecules move faster, leading to quicker propagation of the sound wave. So, as a general rule, sound travels fastest in solids, then liquids, and slowest in gas. For example, it's fastest in steel, which is 5,940 meters per second, and slower in water, which is 1,496 meters per second, and slowest in air, which is 343.2 meters per second. While in a vacuum, with no particles, sounds cannot travel at all.
So now let's move on to the speed of sound in a fluid. We're talking about how sound moves in fluids like water or air. Unlike solids, where vibrations travel in different ways, in fluids, sounds travel as longitudinal waves. This means the particles of the fluid move back and forth in the same direction as the wave. So one way to picture this is by using a piston pushing into a fluid, as shown in the diagram. Look at part A. Here, the fluid is initially in equilibrium, meaning it's balanced. The pressure inside the fluid is same everywhere and nothing is moving. Now in part B, the piston pushes into the fluid. When it moves to the right, it compresses the fluid particles near it. This creates a higher pressure region. The compressed particles then pushed on the next particles, and those pushed on the next. This chain reaction is what creates the sound wave. In the diagram, you see two regions. The fluid near the piston is moving because it's being pushed, and the fluid farther away is still at rest. The boundary between these two regions is moving forward at the speed of sound. This means the disturbance, the compression, travels through the fluid faster than the piston itself. Now, the speed of sound in a fluid depends mainly on two things. The bulk modulus, or the B. This measures how hard it is to compress the fluid. The stiffer the fluid is, the faster the sound can travel through. Density, or the rho. This is how heavy or dense the fluid is. A higher density usually slows the sound down because heavier particles resist movement more. Now let's look at the formula for calculating the speed of sound in a fluid. So the V is equal to the square root of B over P. V is the speed of sound in the fluid, measured in meters per second. B is the bulk modulus, measured in pascals. P, or the rho, is the density of the fluid, measured in kilograms per cubic meter. From this formula, we can see that if the bulk modulus is high, meaning the fluid is very stiff, the sound will travel faster. On the other hand, if the fluid has a high density, sound will move slower. So the speed of sound depends on the balance between stiffness and heaviness of the fluid. Let's now have an example using the sample problem. The bulk modulus of water is given as B is equal to 2.18 times 9, 10 to the power of 9 pascals, and the density of water is P is equal to 1.00 times 10 to the power of 3. We want to find the speed of sound in water. Using the formula, let's divide the bulk modulus by the density, and this will give us 2.18 times 10 to the power of 6. Now let's take the square root, and this will give us 2.18 times 10 to the power of 3. Then the approximate the square root will be 1.476 times 10 to the power of 3. So now the density is at 1,476 meters per second. This means that the speed of sound in water is about 1,476 meters per second. That's much faster than in air, which is around 343 meters per second, because water is less compressible and has a higher bulk modulus.
Okay, so hello everyone. Let's proceed to the speed of sound in a solid. So in a solid rod or bar, sound moves as a longitudinal wave. So this means that the particles move back and forth along the length of the rod. So when we say that the rod is compressed, it means the sound wave inside the rod pushes the particles closer together, so pushing each other forward and a little sideways, which means that solid is special compared to liquid and gases, which ang particles only move back and forth and not sideways. So the speed of sound depends on the medium. As you can see in the table, air is about 344 meter per second, water is 1,482 meter per second, and steel is about 5,941 meter per second. So, which means that it is slowest in gases, faster in liquids, and fastest in solids. So this shows that sound really moves much faster in solid compared to air or water. Now, this is the formula for the speed of sound in a solid. So V is equal to square root of Y over P, where the V is the speed of sound in the solid, Y is Young's modulus, which measures how stiff or hard the material is, and P is the density, which tells us how heavy the material is for its size. Now, are you guys ready to solve a problem? So here is a problem. A steel rod has a Young modulus of 2.0 times 10 to the power of 11 newtons per square meter and the density of 7.8 times 10 to the power of 3 kilogram per cubic meter. Find the speed of sound in the steel rod. So first, let's look for the given values. So we have here with the Young's modulus, or Y is equal to 2.0 times 10 to the power of 11 newtons per square meter, and the density, which is 7.8 times 10 to the power of 3 kilograms per cubic meter, and we will find the speed of sound in the steel rod, or the V. So for the solution, let's look for a formula first. So as we have discussed earlier, the formula is the V is equal to square root of Y over P. So let's substitute the given values. We have V is equal to square root of 2.0 times 10 to the power of 11 over 7.8 times 10 to the power of 3. So we've got here 2.56 times 10 to the power of 7. Now let's square the 2.56 times 10 to the power of 7. Then now we've got a speed of sound in the steel rod, which is 5.06 times 10 to the power of 3 meters per second, or 5,059 meters per second. So that is so easy. You got it right?
Good day everyone, let's talk about the speed of sound in a gas. So let's begin by understanding how sound behaves in gases. So sound in gases travels as longitudinal waves. That means the air particles move back and forth in the same direction as the sound wave, creating compressions and rarefactions. Now, the speed of sound in a gas is not constant. Therefore, it depends on factors such as temperature, the type of gas, and the gas's heat capacity. So for example, now warmer air allows sound to travel faster because molecules move more energetically and collide more quickly. So since gases are easier to compress than solids, sound travels more slowly in gases. That's why we hear sound in air much slower than in steel or water. Still, air is the most common medium we use for hearing sound. Okay, now let's move on to slide 2. Formula for speed of gas. So to calculate the speed of sound in a gas, we use this formula. The speed of sound V equals the square root of gamma times the gas constant R times the temperature T divided by the molar mass M. Here's what each symbol stands for. So gamma is the ratio of heat capacities. For air, no, it's about 1.4. And R is the universal gas constant, which has a fixed value of 8.2014 joules per mole per Kelvin. And T is the absolute temperature, and it is always in Kelvin. And M, the molar mass of the gas. For air, it's approximately 0.029 kilograms per mole. So this formula shows that sound moves faster at higher temperatures and in gases with lighter molecules. So a fun example of this is helium. So in helium, no, the speed of sound is about 1,000 meters per second, almost 3 times faster than in air. So because of that, sound moves faster. So your voice sounds squeaky when you inhale helium, but it doesn't actually change your vocal cords. Instead, it changes how sound waves resonate in your vocal tract, producing that funny effect. Okay, now let's move on to the slide 3, which is the sample problem. So now let's solve a sample problem using this formula. This And okay, so here's the problem, no? Suppose you want to calculate how fast sound waves travel through air on a warm day when the temperature is 20 degrees Celsius. So find the speed of sound in air at 20 degrees Celsius. So now we have identified what is asked when we need to find the speed of sound represented by V in air at a temperature of 20 degrees Celsius using the formula V equals square root of gamma times R times T divided by M. So we have to list the quantities given, no? So the gamma, or the ratio of heat capacities for air, is 1.4, and R, the universal gas constant, is 8.314 joules per mole Kelvin, and temperature is 20 degrees Celsius, which we convert to Kelvin by adding 273, giving 293 Kelvin. So the molar mass of air is 0.29 kilograms per mole. And so let's substitute the values into the formula. Okay, now so place all of these numbers into the equation. So V equals the square root of 1.4 times 8.314 times 293 divided by 0.029. So now first, now let's multiply the gamma, R and T. So 1.4 times 314 times 293 gives about 3,403.3. So now let's divide the molar mass. So 0.29 divided by 3,403.3 is roughly around 117,390. So take the square root, no? So finally, the square root of 117,390, to get the speed of sound, the square root is about 342.7 meters per second. And to round to practical value, we can round this into 343 meters per second. Therefore, on a day when the temperature is 20 degrees Celsius, the speed of sound in air is about 343 meters per second, which is a little over 1/3 of kilometer every second. So this also explains why we see lightning before we hear thunder. So light from lightning reaches us almost instantly, but sound is much slower. So thunder takes about 3 seconds to travel 1 kilometer. So if you count the seconds between lightning and thunder, you can estimate how far away the storm is. Now let's move on to slide 4. Finally, let's compare how sound moves in different media. Okay, so sound requires a medium to travel. So no medium means no sound, like in outer space, but depending on the medium. So sound travels at different speeds, no? In gases, particles are far apart, so collisions happen less frequently. That's why sound is slowest in gases. And in liquids naman, particles are closer together, so vibrations move faster. And in solids, now particles are packed very tightly, so energy transfers very quickly, and then making the sound fastest in solid. So to summarize it all, gas is slowest, liquid is faster, and solid is the fastest. This is why you can hear a train coming by putting your ear to the tracks before you can hear it through the air. And that will be all for the speed of sound in a gas. Thank you.